Now I'm recording. So, chapter 6 deals with polynomials, okay? This is not entirely different from what we were doing, okay? But this is just straight up all algebra now. Like I don't think we're going to be doing much graphing, if any, ever again. All right? You'll see graphing probably later on, but in chapter 6 it's all about polynomials. So section 6.1, adding and subtracting polynomials. Now, I don't think it's fair if I just show you how to add and subtract polynomials without actually telling you what a polynomial is. So, let me ask you a question. Does anybody know what a polynomial is? I mean, what is a polynomial? Here's a little hint. You've been looking at them the entire semester.
I mean, I know it's an expression.
Leah, stop right there. It's an expression. You nailed it. All right, so a polynomial, let me get out a black marker here. It's an expression that contains variable terms, constant terms, and math operations like add, subtract, multiply, and divide. Okay? Now, what makes a polynomial so special, and I'm going to put a star here, the exponent or exponents on the variable terms will always be a whole number. So those exponents are going to be 0, 1, 2, 3, 4, 5, 6, 7, 8, and so forth. All right? You will never have an exponent that's a fraction and it be called a polynomial. That's called a rational expression. It's something different. Okay? Now, we can break polynomials down into like groups. And there's basically 3 or 4 groups. Okay? So let me show you. 4x, or just the variable x, or the number 2, even negative pi, which is a very special number. These are all called monomials. And they're mono, meaning one term, okay? Kind of like, you know, if you're listening to music in stereo, there's 2 speakers. Mono, there's only 1 speaker, all right? Now, the second type of polynomial we have would be something like this. Notice the first one is 3x plus 1. The second one is 2x to the 5th minus 2. The third example is 4 plus x. We call these binomials. Okay, we call them binomials. Bi, just like a bicycle, 2 wheels, 2 terms. Now, in red, I'm going to draw another star because I want us to be aware of this. Terms, regardless if they're variable or constant, doesn't matter. Terms are separated by plus and minus signs. So that's how I looked at those examples and said, oh, 2 terms. The first term is 3x. The second term is a 1. Okay? Any questions? Am I moving too fast? Or are we okay? All right? Perfect. Now, the third type of of a polynomial is this. All right. Who wants to take a stab at this name?
Trinomial?
Perfect, Craig. These are called trinomials. Tricycle, three wheels, 3 terms. Okay? Now, there's a reason why we need to know these names here. And it's because depending upon what I give you, there's going to be a technique associated with it. So, for example, when we get into chapter 7, and I know many of you may have heard this word before, chapter 7 is called factoring. How many of us have heard that before? Factoring. Well, depending upon the polynomial given, there's a different factoring technique. There's a different factoring technique if you're factoring binomials. There's another technique if you're factoring trinomials. So it's extremely important that we know the difference between a monomial, a binomial, and a trinomial. Anything larger than a trinomial is called a polynomial. All right? So anything bigger than a trinomial, so 4 terms, 5 terms, 6 terms, and so forth, they're called polynomials. And the reason for that, and I don't even know if this is the reason. I am literally just, this is me thinking out loud here. The reason why we really don't give them too many names is because once you get into these higher order polynomials, there is just one technique that we use to try to factor them. And it deals with the rational root theorem and the remainder theorem and all that stuff you would learn in MAT090, which is pre-calculus. If you took that with me, we would go over stuff like that. Okay? The basics, monomial, binomial, trinomial, and they have techniques. All right? The larger polynomials, they tend to get very, what's the word here? Very, very confusing. And there are techniques like Ferrari's theorem. It's not just a car; it's an actual. Ferrari was a mathematician. I think there's another one. I can't remember all of them. I took when I was on your side of the desk, I took a class called Theory of Equations, where all we did was study equations and their forms and stuff like that. If you're not a math person, it's a very boring class. If you were like me, you couldn't wait to go to class because it was like, oh, I'm going to learn about polynomials. I'm thinking out loud again, right, Megan H? I mean, when you guys think about me, you're like, man, that floater, he's great. Or, that guy really likes math, I can tell you that. All right, so here we go. The next thing we're going to talk about are degrees of a polynomial. How's my handwriting today? I feel like it's really good. I'm having a good handwriting day. So, degrees of polynomial. First, the degree of a term. This is important. The degree of a term is the sum of the exponents of its variables. All right? So, examples. The first example is a monomial. Its degree is a 3. And that is because the exponent is to the 3rd power. So we say its degree of 3. Here's another example. A plus 7. Now this is a binomial, but the degree is going to be a 1 because that A is raised to the 1st power. Let's look at one more example here, okay? The degree of this term is 8. Because when you add the exponents together, that z is raised to the first power. 5 plus 2 is 7, plus 1 more is 8. So it's a degree of 8. Does that make sense, everyone? Okay? The next definition is the degree of a constant. The degree of a constant is 0. Okay? That's all you got to know. Degree of a constant is 0. So an example, 7. Degree equals 0. I think that's the easiest one, okay? Now the last one, you cannot confuse with the first rule. So the last one is the degree of the polynomial. So now we're not just looking at the individual term, we're looking at the entire polynomial as a whole. So the degree of a polynomial is the highest degree of all its terms. Okay, it's the highest degree of all of its terms. So let me show you an example because I want to make sure we understand the difference. All right, so here's an example here. 3x, or 3 times x to the 8th, minus x to the 5th times y to the 7th, plus 2 times x, y to the 4th. Now, if I was looking at just the degree of the terms, each term I'm going to write its degree underneath. So the first one is going to be an 8, the second one will be a 12, and the third one will be a 5. Does that make sense? The degree of the polynomial is a 12th degree polynomial. So it's the highest degree of the terms. So terms can have their own degree, but the degree of the polynomial will tell you this is the highest. All right. Are there any questions there? All right. Traditionally, we will write polynomials in descending order of degree. Like that's what I'm going to be doing. So if I give you something like this, negative 4x plus 3x to the 3rd minus x to the 4th. If you were to look up the answer in the back of the book, the answer would say, okay, we're going to rewrite it in highest degree first, and then in descending order. We call that standard form. Are there any questions? All right. So now that we understand what a polynomial is, the degrees of the polynomial, degree of the terms, how do we write them, we can finally get into adding, subtracting polynomials. And here's the best part. You already know how to do it. There is nothing new I'm going to be teaching you here. And the reason why I say you already know how to do it is because all you need to know is combining like terms. That's it. And how do we combine like terms? There are two steps. What are they? Or not, I don't want to say steps. There are two checks you need to pass before you're allowed into the party of combining like terms. What's the first check?
Same variable.
I love it. Same variable. What's the second check?
Same exponent.
Bingo. So as long as you pass those two checks, excuse me, you will be allowed to come to the combining like terms party. And trust me, it's an awesome party. There's pizza, there's wings. I love wings. I am not allowed to eat wings inside my house. My wife does not like it. She says it's disgusting. So I eat them outside the home, or I sneak them. Now, I don't know how you eat wings. I just kind of just put the whole wing in my mouth and just pull it out. My wife just made a noise. She's upstairs. She literally, I just said that and she goes, bleh. Anybody else like wings? Dylan, you're shaking your head. Yes. Do you have a favorite flavor?
I love buffalo.
Hot buffalo is all me. Hot buffalo, some ranch dressing on the side. All right. All right. So let's go ahead. Let's combine some like terms, okay? So here's our first example. So we have negative 15z to the third minus a negative 5z to the third. First, what type of polynomial is this? It's a binomial. Excellent, Wesley. Wesley, is there anything about this problem that you're looking at? You're like, oh, I could do this first. I might as well do it. You see anything?
The two minus signs to equal positive.
I love it. Anytime you have signs back to back, traditionally, just rewrite it to make it look prettier. So we got negative 15z to the third plus 5z to the third. Now, here's the question. We want to add these together, and we know if we combine like terms, we got to pass two checks. First, same variable. Well, they both got the same variable. It's the letter z. But now, they also have to have the same exponent. And in this situation, they both have a 3. So I know I can combine these two. So I could care less about that variable. What I'm concerned with, what's negative 15 plus 5? Love it. So there's your first answer. Negative 10z to the third. Does that make sense, everyone? All right. I agree with you, Amy. Very standard, easy problem. Thank you. I could read your mind. It's exactly what you were thinking, right? I knew it. So here's the next one. Add 8y to the second plus 4z to the second minus 4y to the second. All right. This is a trinomial. So what I'm going to be doing is looking for like terms. Do we see like terms, yes or no? I agree. Right there, you have 8y to the second. All the way to the right-hand side, you have minus 4y to the second. Same variable, same exponent. So let's combine them together. 8 minus 4 is going to be 4. Y to the second plus 4z to the second. Nothing, I cannot combine those two because they have different variables. How are we looking so far? Pretty good? All right. This next problem will be the easiest one of the day. If I wanted to combine this, if I wanted to subtract 3x to the second minus x minus 1, even though the first two terms have a letter x, they do not have the same exponent. Therefore, I cannot combine them. And this negative 1 all the way on the end, that's just a constant term. So, can I combine anything here? Yes or no?
Nope.
Nope, I agree, Dylan. So we just circle it. Game over. The only way I can make this, I guess, a little bit more difficult is if I give you something like this.
Can I ask, if you put a question like that on a test or homework, would we put no solution or would we just rewrite that?
You would rewrite it. Okay? So here's our last problem. 5m to the third, n to the second, minus 4, n to the second, n to the third, plus 5. Let's do another number. We'll do 11. N to the third, n to the second, minus mn. Like, this is the only way I can make it harder, is by giving you more complex terms for the polynomial. But you know the rules for combining like terms. Same variable, same exponent. So if I look at the very first term right here, that is 5m to the third, n to the second. So what you need to be able to do is just scan all the other terms and say, okay, do I see any other terms with m to the third, n to the second? The answer is yes, it's right here. So once you've established, oh, same variable, same exponents, 5 plus 11, well, that's going to be 16. M to the third, n to the second. Now, that minus 4m to the second, n to the third is different. But there are no other terms that look like that. So I just rewrite it. And that minus mn at the very end, we're going to leave it at the very end. And there's our answer. Does that make sense, everyone? Good, good. Let's keep pushing then. We'll keep going. We don't have too many more things to do. All right? Now we're going to start getting into more complex problems that we got to do something first. All right? Here's what I'm talking about. All right. So if I go ahead and read this, this is read, the quantity of 7x to the second plus 4x minus 2 minus the quantity of 3x to the second minus 4x plus 2. So the first thing that I need to do here is, because I see those parentheses, I got to distribute first. And that is the key to this. All right? So if we think about the very first quantity, the 7x squared plus 4x minus 2 polynomial, or in this case, trinomial, technically there is a positive 1 out front. So you would have to distribute the positive 1 to every single term. However, multiplying anything by positive 1, it just remains the same. It's the second trinomial I need to be concerned with. And the reason for that is there's a negative sign out front. So I need to distribute the negative sign. So I'm going to write minus 3x squared plus 4x minus 2. Does that make sense, everyone? Okay? If you make a mistake, that's where it is. From here, we're going to combine like terms. So, as you can see here, these problems tend to start getting very long, horizontally, left and right. All right? I don't care what you do to help you see things. Some people use highlighters. Some people will use colored pencils. Other people will draw lines underneath. I know those two terms are like terms. 7x squared minus 3x squared. Well, that's going to be 4x squared. 7 minus 3. Then I will look here at the plus 4x. Now I put 2 lines underneath it because I know that's different from the previous. But notice off to the right, I have another like term. 4 plus 4 is 8. X. The last thing I got to worry about are my constant terms. -2 minus 2 is -4. Notice, by me taking my time, keeping things in order, looking for the highest degree, not only did I combine like terms correctly, but it's also in descending order, which is what I want. Highest exponent first, then write them in descending order. How are we looking so far? Pretty good? Okay. Let's do another one. You're going to do it this time, okay? I'm not going to do it. You're going to do it. Try that one. Okay. Did anybody get an answer?
No. No.
Okay. I'll wait a minute. No problem, Craig. Sometimes I forget we're learning this. Takes us a little bit more time, and that's fine. All right, how are we looking? Pretty good?
Yeah.
All right, we got an answer?
Yes, sir.
What do we get?
6b squared minus 5b plus 3.
All right, I love it. Let's just go ahead. Let's do it, though. So remember, for the first trinomial, there is a 1 out front. So we're going to distribute. For the second trinomial, there's a second binomial. So let's make sure we distribute appropriately. So you're going to get -3b squared plus 7. And now it's just a matter of combining like terms. 9 minus 3 is 6. B to the second. Now this -5b, there are no other b to the first terms. So it just comes along for the ride. -4 plus 7, +3. We good? All right. So the last thing I want to go over is evaluating polynomials. All right. Am I moving too fast? Are we okay?
Good.
All right. So here's a question right here. And it actually happened over the weekend. So here's the question right here. The polynomial, so it's a word problem. I know we love word problems. The polynomial -16 t to the second plus 250 gives the height of a football after t seconds. So the variable t is measured in seconds, okay? Find the height of the football after t equals 3 seconds. All right. Now, we will be kind of exploring some of this later. okay? But if I were to grab Desmos, and I got to zoom out here before I type it in. There we go. And I were to just type this in, negative 16. Now remember, I got to use X. And let me just change this real quick. We're going to go from negative 5 to, let's say, 15. Well, why did it? There we go. So these exponents when they're a number 2, okay, like the example we have, we call this shape right here in red, we call this a parabolic trajectory. If you think about it, you do it every single time when you throw something. When you throw something, the object goes up and then it comes back down. All right? Now, I said this happened over the weekend. Did anybody happen to watch the Baltimore Ravens and Detroit Lions game? Dylan, what happened at the very end of the game?
They kicked a 66-yard field goal.
It was phenomenal. Now, number one, to be able to kick a football that far is crazy to begin with. Professionals do it, not the local guys like myself. However, and this is my great artistic ability here. All right, so there's the football right there. Not only did he kick the football 66 yards, but it actually hit the goalpost and bounced over. So it was a good field goal. Now, I don't know if you're a sports fan, but you live for stuff like that. Because it's just so awesome. You're like, oh my gosh, you did it, right? But I want you to look at the trajectory here. It's parabolic. It is just like this. So if you were watching the football game, you could actually sit down, take a screenshot, and you can figure out exactly what that equation was to give you that football trajectory. This is just a simple example of what's happening. So when we see the words evaluating polynomials, what we are really thinking of is substituting in and simplifying. So what I like to do is rewrite the problem. You know me, I'm old school. Directly underneath, I will put my parentheses, and then I make my substitution. Now, according to our order of operations, you need to do the work inside parentheses first. However, the number inside the parenthesis, or the thing inside a parenthesis here, is just a number. There's nothing you can do. So parentheses are done. The next thing you do are exponents. So, negative 16 times 3 to the second power is 9. Exponents are done. Now remember, you do multiplication and division in order from left to right. I don't know if we remembered that, but you do it in order from left to right. So, negative 16 times 9 is negative 144 plus 250. So multiplication and division are now done. And negative 44 plus 250 is 106. So, since they asked for the height of the football, we're just going to say 106 feet in the air. All right? Which, that's pretty high. All right? I mean, if you think about it, when a punter punts a football, considered a really good hang time, meaning the ball is in the air, is around 5 to 6 seconds. The closer to 6, the higher the ball was. You just hope that he kicked it really far and not really short. Okay? Are there any questions? All right, well, Chapter 6, Section 1 is officially done.